Start recording here. Okay. So complex number in standard form, A is the real part, BI is the imaginary part, and all real numbers are complex numbers. The pure imaginary unit is defined to be the square root of -1. Okay. All right, so let's begin to perform operations on complex numbers. All right, so the first thing we're going to look at, ladies and gentlemen, is this right here. How to simplify the square root of -100. Okay. Now, up to this point, we said the square root of a negative number is undefined because we were confined to the set of real numbers. But now, ladies and gentlemen, we're broadening our scope this afternoon. We're now sitting in a much larger set of numbers called a set of complex numbers. So the square root of -100 is not just something we just, throw under the rug and say can't do anymore. Let me show you how we would simplify the square root of a negative number in general. In general, if I have the square root, if I have the square root of a negative number in general, do you agree I can rewrite the square root of -a as the square root of -1 times a? We all buy that? But the product rule of square roots says that I can break this up into the square root of -1 times the square root of a, correct? But ladies and gentlemen, what's the definition of the square root of -1? What is the square root of -1?
I, the imaginary number.
I, yeah, the pure imaginary unit, I. So the square root of -1 is I. And so this is what we got going on here. So ladies and gentlemen, when you have the square root of a negative number, to make this long story short here, you just want to remember that you can always bring I out from underneath the square root. And I'm showing you why that's the case in general here, okay? So when you have the square root of a negative number, we can bring I out. Then it's I times the square root of the positive of that number. Now, what's the square root of 100?
10.
So this simplifies to 10i. Now, with your calculator in complex number mode, ladies and gentlemen, convince yourself, take the square root of -100 on your calculator. Remember, your machine's in what? Complex number mode, correct? It should be. So take the square root of -100, and what do you get?
10i.
You get 10i. Okay, see that? You get the imaginary number called 10i. All right. So again, when you have the square root of a negative number, you can always bring I out, and then it's I times the square root of the positive of that number. Let's try another one. Let's try to simplify this expression here. The negative of the square root of -25. So it's like the opposite of the square root of -25. Because we have a negative, not outside, we don't care about that, but because we have a negative underneath our square root, I can bring out I. So this is really going to be equal to -I times the square root of +25. Now, what's the square root of 25?
5.
So this simplifies to -5i. You see that there? That's what that simplifies to, is -5i. Right? What if we want to multiply two square roots with negatives underneath them? If I want to take the square root of -10 and multiply it by the square root of -5, and I wanted you to wait a minute, the square root of -5. I didn't want the square root of -50, square root of -5. All right, so if I want to take the square root of -10 and multiply it by the square root of -5, and then I want you to simplify this expression, what do we do? Well, ladies and gentlemen, we got to be careful here. Before you actually multiply now you cannot apply the product rule and say this is a square root of -10 times the square root of -5, which is a square root of 50. That's no good. The reason why we cannot use the product rule is because the product rule applies to real numbers. These are not real numbers. These are imaginary numbers. So what you need to do first, before we actually multiply the radicands together, you need to extract I out from underneath both these square roots. So the square root of -10 is just I times the square root of +10. Similarly, the square root of -5 brings out I times the square root of +5. So you got to bring out I first. Now, what's I times I?
2i.
No, not 2i.
-1.
I squared?
Yeah, it was right for the present moment, I times I is I squared. And now we can multiply the square root of 10 times the square root of 5, since these are real numbers, and the square root of 10 multiplied by the square root of 5 would net us the square root of 10 times 5, or the square root of 50. But look at, remember, by definition, I was a square root of -1. So ladies and gentlemen, what do you think I squared is always going to be equal to?
-1.
Yeah, it will be -1. Okay, so these are facts you just want to lock away in the memory banks. All right. So therefore, I squared is replaced with -1. So therefore, we have -1 times the square root of 50, which is just to say the negative of the square root of 50. Can I further simplify the square root of 50? Is it harboring any perfect squares? Well, 50 is not a perfect square. However, 50 can be factored down into 25 times 2, and 25 is a perfect square of 5. So this 25 is going to come out from underneath the square root when we take a square root as a 5. So we're going to have -5 times the square root of 2. And that's what this would simplify to. So the square root of -10 multiplied by the square root of -5 simplifies down to just -5 times the square root of 2. Any questions how we negotiated that problem? The key is, first of all, you got to bring out I from underneath these square roots, because these are not real numbers, right?
How did we get rid of the I squared? I'm sorry.
Okay, I squared, if I is the square root of -1, and if we square both sides of this thing, we're going to have I squared being what? -1, then, correct?
Oh, okay, yes, yes.
So we just replace I squared with -1, and I just
Okay.
put it down as a negative sign there. You could put -1, but it's just a negative sign, right?
Okay, thank you.
Any other questions, ladies and gentlemen, how we're negotiating these so far? All right. Okay. Let's, we all have this accounted for here, this page. Okay, let's try, what if I want to simplify the square root of -45 divided by the square root of -5. All right. Again, ladies and gentlemen, because we have negatives underneath our square roots, what must we bring out first, even before we try to do any sort of division or anything?
The negative?
Well, yeah, you bring the negative out in the form of what, though?
Oh. Flip them?
No, when you got the square root of a negative number,
You
we
take
always,
out I.
yeah, we always got I, correct? We bring out I, and it's I times the square root of the positive of that number then. Square root of -5 is going to be I times the square root of +5. So again, whenever you have the square root of a negative, always bring I out first. All right. These I's will reduce now, and then we're left with just the quotient of two real numbers, the square root of 45 over the square root of 5. Now we can evoke the use of the quotient rule of radicals and rewriting this as a square root of 45 divided by 5. And this simplifies the square root of 9, which just simplifies down to just what? Just 3, and that would be your answer. Okay. So again, just try not to forget, when you have a square root of a negative, always bring I out first, and then it's times the square root of the positive of that number. Bring out I first, and then take care of your operations. All right. Okay, suppose that I want you to write the following in standard form, A plus BI form. So this is standard complex number form, and I give you 6 subtract the square root of -24. How would I, ladies and gentlemen, write this in standard complex number form, A plus BI form? Well, what's the first thing we would do here? Anybody?
Bring out the I.
Yes, we have a square root of a negative number, so we want to bring I out first. So this is going to be equal to 6 subtract I times the square root of 24, positive 24. And now the only thing that remains is simplifying the square root if possible. Any perfect squares underneath there? 24 can be rewritten as 4 times 6. The wisest choice for the factored form of 24, and the square root of 4 brings a 4 out as a what? 2. 2 comes out and joins this I as a factor. So we got 6 minus 2I times the square root of 6 that remains underneath. Okay. And this is it. We have rewritten this in the form of A plus BI. Now you're probably wondering why we don't put the I at the end. Here's why, ladies and gentlemen. when you have a radical times I, you want to put I in front of the radical, because look at, if you don't, if you put I at the end, if you're not careful, it might look like I is what? Underneath the what?
Square
The
root.
square root, when it should not be underneath the square root. So to avoid this possible ambiguity, ladies and gentlemen, if you have I times a radical, make sure you have I in front of the radical, okay? It's common practice. There we go. All right, so far pretty good. Let's try to write this expression in standard complex number form. 9 minus 15i divided by -3. How would I write this in standard form, a plus bi form? Anybody? What would we do here? Do you agree I can place each term in the numerator over the what? The -3? So let's put the 9 over the -3 plus, and let's put the -15i over -3. Now all we have to do is reduce. This reduces down to -3. -15 divided by -3 is a +5. Ladies and gentlemen, I now have my number written in what? Standard form, as far as a complex numbers form is concerned, correct? -3 plus 5i. So we went from this form to standard form, all right? Just as we were asked to do so. Any questions about any of these on here so far, ladies and gentlemen? Performing some operations involving complex numbers or imaginary numbers, all right? Okay. Let's see here. Let's try to do this one. Write in a plus bi form. And this comes at us as -10 plus the square root of -125 over 5. We want to write it in standard form. First thing you might want to do is just bring out I from underneath the square root of this negative here. We can split this up now, put -10 over 5, plus we can put I times the square root of 125 over 5. This reduces down to -2. 125 is not a perfect square. However, 125, ladies and gentlemen, is rewritable in factored form as probably the optimal way to write 125 in factored form is to say 25 times 5. And this still sits over 5. Now look at warning, you cannot cancel these 5s out. This 5's underneath the square root, this 5 is not. Don't cancel these 5s out. But the square root of 25 brings a 25 out as a 5, and that 5 will come out from underneath the square root and join the I. Now, these 5s can be reduced. Not these, but these 5s can be reduced. So our final result is -2 plus I times the square root of 5. And ladies and gentlemen, we have accomplished our goal of rewriting this in standard form, a plus bi form. All right. Questions so far? All right, what if we want to simplify I raised to very big powers? Suppose I wanted you to simplify I raised to the 50th power. I raised to the 50th power. Well, ladies and gentlemen, what do we know about I? We know that I squared is always equal to what?
-1.
This is a fact, correct? We can use this fact to help us simplify I to the 50th power. Specifically, we ask ourselves, how many perfect squares of I are in I to the 50th power? Take 50 and divide it by 2. Take the 50 and divide it by 2 to find out. 2 goes into, 2 goes into 50, what, 25 times? Nothing left over. So, ladies and gentlemen, in I to the 50th power, there's really 25 perfect squares of I, meaning I can rewrite I to the 50th power as I squared to the what? 25th power? You all buy that?
Yeah.
But what's I squared?
-1.
-1. So this is really -1 to the 25th power. And lay down the way it works when you raise -1 to a power is this. -1 raised to an integral power is equal to +1 if the exponent integer is even. It's equal to -1, however, if the exponent n is odd. So what's -1 to the 25th power going to be? Positive or -1? 25 is an odd power. So this is going to be what? -1. That's right. So I to the 50th power simplifies to -1. So I to the 50th power simplifies to -1. Let me see how we did that one there. Let's try I to another big power. Let's try, ladies and gentlemen, let's try I raised to the 187th power. Let's try to simplify I raised to the 187th power. Again, we're interested in how many perfect squares of I are in I to the 187th power because we know this fact. To find out, we take 2 and divide it into 187 to find out how many perfect squares of I are in I to the 187th power. 2 divides into 18 9 times. Bring down to 7. 2 divides into 7 3 times with a remainder of what? 1. So in I to the 187th power, how many perfect squares of I are there? There are
93.
93. So we can rewrite this as I squared to the 93rd power times, ladies and gentlemen, but look at, we got 1 I left over. We got a remainder of 1. So that means times 1 I left over. Remainder of 1, 1 factor of I left over. Now, what's I squared? By definition, I squared is what? -1. So we replace I squared with -1. So we got -1 raised to the 93rd power times I. Now, -1 being raised to an odd power will be positive or -1? What do you think?
Negative.
-1. So we got -1 times I, which just simplifies down to -I. So believe it or not, I to the 187th power simplifies down to just -I. -I. All right. All I need to show you remaining is how to add and subtract complex numbers, how to multiply them, and how to divide them. And then we're done with this section. All right, any questions, ladies and gentlemen, how to simplify I raised to a very big power? What would be I to the 250th power? Well, how many perfect squares of I are in I to the 250th power? Divide 2 into 250.
125.
And yes, there will be 125. So there's 125 perfect squares of I in I to the 250th power. I squared is replaced with -1. Raised again to an odd power would give you what? -1, correct? Give me -1. Is our answer always going to be -1? What if I have I to the what if I have I to the 28th power? How many perfect squares of I are in I to the 28th power? Divide 2 into 28 and find out. 2 goes into 28 14 times, right? With a remainder of what? 0. So I to the 28th power can be rewritten as I squared to the what? 14th power. But ladies and gentlemen, I squared is -1. Now what's -1 raised to an even power? Positive or -1 now? Raised to an even, +1. +1. So I to the 28th power simplifies to +1. All right. All right, let's put that away. Ladies and gentlemen, how do we add and subtract complex numbers? First of all, do we have this accounted for? Remember, this is being recorded also, so you'll be able to see the recording, which you can watch at your leisure. All right, how to add and subtract complex numbers. All right, so adding and subtracting complex numbers, how do we do it? Well, in general, suppose I have a complex number a plus bi. And to that, ladies and gentlemen, suppose I want to add another complex number called C plus DI. Both these complex numbers are in standard form. What's the do's and don'ts when it comes to adding two complex numbers together? Well, the do's is we can only add the real parts together. So A can get added to the C because these are the real parts of the two complex numbers. So A gets added to C plus, and then the imaginary parts can only be added together. So B gets added to D, B added to D times the imaginary, pure imaginary unit I. This in general shows us how we add complex numbers together. We can only add the real parts together to get a real part, and we can only add the imaginary parts together to get an imaginary part. This is also true for subtraction. If you have some complex number in general, A plus BI, and you want to subtract off some complex number, C plus DI, we can only subtract the real parts. So A subtract C is legal, plus, and then we can subtract the imaginary parts, B subtract D times I. So in a nutshell, ladies and gentlemen, this is instructing us how we would add or subtract complex numbers, okay? So just remember, you can only combine like parts, if you will. You can only combine the real parts and the imaginary parts. Real parts and the imaginary parts, okay? So don't try to add a real part to an imaginary part. Can't do that. All right, well, let's try our hand at one here. Okay, so let's try. So if I have like the complex number 250 plus 100i, and I want to subtract off the complex number 80 minus 25i, how do we subtract these two complex numbers? Well, we can only subtract the real parts, so 250 will subtract off 80. Plus, and then we subtract the imaginary parts. 100i subtracts a negative 25i, specifically 100 minus a negative 25. And that'll be your I there, okay? Okay. Jackson, we are going over complex numbers in section 1.3. Right, 250 minus 180 is going to be what?
170.
170. 100 subtract a negative 25 is 100 plus a 25, which is plus 125. And that would be the difference between these complex numbers here. 170 plus 125i. You know, ladies and gentlemen, you can do this on your calculator. You can subtract complex numbers on your machine. I'll show you how to do this problem on your calculator. So let's show you how to subtract complex numbers on your calculator. We have 250 plus 100i inside parentheses, 250 plus 100. Now we got to go get I. Where does I hang out? Well, I hangs out, where is I? I used to know where I was. What the heck? Hold on a second here. I believe is,
Why did X square it?
it's above your decimal point. Above your decimal point key, ladies and gentlemen, in blue. So I have to hit my second key, followed by my decimal point key, and I bring up I. Everybody see that there? I is above your decimal point key. So we have 250 plus 100i, and we want to subtract off the complex number 80 minus 25i. Hit enter, and you get your result, which is 170 plus 125i. So that's how you can add and subtract complex numbers, and even multiply and divide them to check your answer on your calculator. Again, I hangs out above your decimal point key. So you have to precede your decimal point key with your second key to access I. Okay. All right, so that's how we add or subtract complex numbers. You know, like if I have 12i plus 16 plus 20i. And I want to add these complex numbers together. Ladies and gentlemen, what's the real part of 12i? What's the real part of 12i, this complex number? Yeah, we don't see any real part. So 12i is really understood to be 0 plus 12i. Same thing. It's just that the real part of 12i is 0. All right, so adding these together, we add our real parts together. We got 0 plus 16 plus, and our imaginary parts get added together, 12 plus 20 of these i's. And so we're going to have 16 plus 32i, and that would be the sum of 12i and 16 plus 20i. Okay. All right, done with that one. All right, just put that away. Ladies and gentlemen, how do we multiply complex numbers together? Multiply. Multiply complex numbers. Well, in general, if I have a complex number a plus bi, suppose I want to multiply this complex number by another complex number, c plus di in general. How do we do it? I'll tell you what, we're going to borrow an algorithm we used so many times in the past. Anybody remember the name of that algorithm? What do you think we're going to do with this to multiply these complex numbers together? It's kind of like multiplying two binomials together, ladies and gentlemen. We're going to use what algorithm?
Foil.
FOIL. A times C is the real number AC. A times DI is ADI. Multiply the inner terms together. BI times C is plus BCI. Multiply the last terms together. BI times DI is plus BD. But what's I times I?
I squared.
I squared at the end. Don't forget that. All right, ladies and gentlemen, AC is just a real number. When you multiply two real numbers together, you get a real number. This is some other real number. So we got a real number. These are called like radicals. Why am I calling them like radicals? Because they both contain I. I is a radical by definition. It's the square root of -1. So what's ADI plus BCI? Well, we can add them together. They're like radicals. So that's really AD plus BCI. BDI squared is what? I squared is what by definition?
-1.
So BD times -1 is negative BD. BD times I squared is -1 times BD. I squared is -1. But ladies and gentlemen, AC and negative BD are real numbers, so they can be combined to simplify this. So we have AC minus BD. That gives you the real part of our product of these two complex numbers. And here comes the imaginary part, AD plus BCI. This is your real part. This is just a real number, and this is your imaginary part. Do you agree? Of our product of these two complex numbers up here. That in general instructs us how we multiply complex numbers together. So maybe we can try one out. Let's try 2 subtract 5i, take this complex number and multiply it by 8 plus 2i. All right, so let's just follow along here. We FOIL this out. 2 times 8 is 16, plus 2 multiplied by 2i over here is plus a 4i. Negative 5i times 4 is minus negative 5i times 8, my bad, is minus 40i. And what's negative 5i times 2i?
10I squared.
Negative 10i squared. Yeah, don't forget I times I squared. We want to simplify this, ladies. Don't leave this looking this way. We got 16. These are like radicals. They need to be combined. What's 4i subtract 40i?
36.
It's 36i. And you agree that negative 10 times I squared is going to become what number?
Negative.
Negative 10 times -1. I squared replaced with -1 is what? Plus a 10. Finally, what's 16 plus 10?
26.
You got your final answer, ladies and gentlemen. This would be the product of these two complex numbers written in standard form. 26 minus 36i. Pretty simple how we're multiplying complex numbers together. It's kind of using like the FOIL algorithm of multiplying two binomials together. And you can check your answer on your calculator. Why don't we try to do this problem on our TI-84 and convince ourselves we get that product there? I always like to have a happy marriage between the class, the manual way of doing things, and the calculator way. Let's try this out on the calculator. All right, so first we type in our first complex number, which is going to be 2 minus 5i, 2 subtract 5. I is second decimal point key, times, you don't even have to put times, you can just put an open parenthesis next to the closed parenthesis. Your calculator understands it's multiplication. I explicitly put multiplication in there, times 8 plus 2i. And ladies and gentlemen, here's your product, 26 minus 36i. That's what we got when we worked it out the long way. Your calculator's got to be obviously in what? What mode to be doing all this? It needs to be in not real mode, but what mode?
Imaginary number mode.
Complex number mode, A plus BI mode, okay? And we did put our calculator in that mode. Please do leave it in that mode, all right? Just leave it in that mode here. All right, let's try to multiply these together here. We have 2 plus the square root of negative 7, and we want to multiply that by 10 plus the square root of negative 7. Well, ladies and gentlemen, we got to bring out I since we have a negative underneath our square root. So we got 2 plus I times the square root of 7 times 10 plus I times the square root of 7. Now we can multiply these together. Remember, always bring out I first when you have a negative underneath the square root. Bring out I. And then times the square root of the positive of that number. Now we just FOIL this out. 2 times 10 is going to give us 20. 2 multiplied by I square root of 7 is going to be plus 2I square root of 7. 2 times I square root of 7, 2I square root of 7. What's I square root of 7 multiplied by 10? 10I square root of 7. And what's I square root of 7 times itself? I times I is I squared. And what's the square root of 7 multiplied by itself? It's the square root of 7 times 7, or the square root of 49. But what's the square root of 49? 7. So it's going to be plus 7i squared at the end. Simplifying, combining the two middle like radicals, 2i squared of 7 added to 10i squared of 7 is going to be 12i squared root of 7. 7 times I squared is really 7 times a negative 1, which is going to be a minus 7 at the end. Finally, 20 subtract 7 is 13. And you got your answer. All right, that's it. Do we see how we're multiplying complex numbers together here? What's special about these complex numbers here? What's special about these complex factors here, ladies and gentlemen? You recognize what's going on? They're called what of each other? The word starts with the letter C. They are called
Conjunctives.
conjugates. Yeah, these are conjugates of each other, right? So ladies and gentlemen, if you have a complex number A plus BI, its conjugate is A minus BI. These are called complex conjugates. Complex because they're complex numbers, and they're conjugates because the difference between them is the sign in between the terms. Complex conjugates. So when you multiply these complex conjugates together, you can FOIL this out the long way if you want, but that's a waste of time. Ladies and gentlemen, in general, when we multiply conjugates together, do you remember what the product is always going to be?
Cancel it.
Just the difference between the what? The squares of the terms? Isn't that true? So to multiply these complex conjugates together should be pretty easy if you can just remember this pattern, this. So it's just the square of 5 minus the square of the last term. The square root of 5 is 25. And what's the square of I square root of 3? That's I squared of 3 times itself, I squared of 3. I times I is what? I squared. Square root of 3 times itself is a square root of 9, which is just what, 3? So the product of these complex conjugates is going to be 25 minus 3i squared. But ladies and gentlemen, I squared is -1 now. Replace I squared with -1, and we really have 25 minus 3 times -1, which is 25 plus 3, which is 28. So the product of these complex conjugates nets us a result of 28. All right, one last operation, ladies and gentlemen, is how do we divide complex numbers? Does anybody remember doing some of these operations that I've been doing here in a previous class? If you've had intermediate algebra, you should have dabbled with all this. Anybody remember this?
I remember the I just
Okay.
don't, now that we're doing it, of course.
All right, so maybe there was a little rust that set in if you did it before, but anybody else remember working with I and operations with I here?
Yes.
Yeah, I mean, if you had intermediate algebra, I know here at Mott, I know we drag you through complex numbers, ladies and gentlemen. So this really should be review. It really should be review if you've had intermediate algebra. If you never had intermediate algebra, it's not review. It's brand new. All right, how do we divide complex numbers? Well, let's try our hand at one here. So in general, if I got like a complex number a plus bi divided by some other complex number c plus di.
When you get a second, can you put the other numbers back up? Tony asked, she didn't get to finish it.
That was
Please.
right here.
I believe so.
Okay, multiplying some complex numbers together. All right, I'll get in the habit of trying to post the recorded lectures also online. I think I got that down now, or my computer's able to do it. But how do we divide complex numbers in general? Well, I claim that this is not considered to be simplified. Why not? Because I claim, ladies and gentlemen, we have a radical where we should not have a radical. Where is that? Where is the radical hanging out where it should not be? Anybody? Recall I is really equal to the square root of what? -1. It's a radical. It's a square root. Where should we not have a square root in this expression? Anybody?
On the bottom.
In the denominator. That's right. We were taught never to leave a radical appearing in the denominator of a fraction. Ladies and gentlemen, we have to get rid of this I down here. That's really how we're going to, divide these complex numbers, is we have to get rid of this I. The only thing that's going to knock this I out down in our denominator is by multiplying the top and bottom of this fraction by the complex conjugate of c plus di. So the only thing that's going to knock this out is multiplying the top and bottom of this by the complex conjugate of c plus di. And what's the complex conjugate of c plus di? C minus di. Exactly. That's what you would multiply the top and bottom of this by. So the moral of the story is, in order to divide complex numbers, ladies and gentlemen, our concern is we always have to eradicate I in the denominator. That's how we divide complex numbers. Okay. All right. And in general, then you would go from here. All right. Let's just look at a specific case here. So 5 plus I divided by 4 minus I. So we want to divide these complex numbers. Now, again, remember what I said, to divide complex numbers, our concern is always to get rid of I in the denominator. That's our concern. By doing that, we will have divided 5 plus I by the denominator. Okay. So how do I get rid of I in my denominator?
Times by 4 plus I.
Yeah, we multiply the numerator and denominator of this by the complex conjugate of 4 minus I, which is to say we're going to multiply top and bottom of this thing by 4 plus I. 4 plus I is the complex conjugate of 4 minus I. All right, let's take care of the business now. We got in our numerator, we got 5 plus I that has to be multiplied by 4 plus I. And downstairs, ladies and gentlemen, since these are complex conjugates of each other, we don't have to FOIL this out. It's just a matter of squaring the first term, subtracting the square of the last term. 4 squared minus I squared is the product of these two complex conjugates down here. All right, in the numerator, we have no choice to FOIL this out though. So 5 times 4 is 20, plus 5 times I is 5I, plus I times 4 is 4I, and I times I is plus an I squared. And this all sits over the product of our complex conjugates, which is 4 squared minus I squared. 4 squared being 16 minus, what's I squared? -1, right? I squared is replaced with -1. Notice I's gone on our denominator. We rationalize our denominator. So cleaning up the numerator further, we got 20 and 5I plus 4I, and that's us what? Plus 9I? Plus I squared. But what's I squared?
-1.
Plus a -1. Downstairs, we got 16, subtract a -1, which is 16 plus 1 or 17. Continuing to simplify, we got 20 plus this -1 over here is 19. So we got 19 plus 9I over 17. And ladies and gentlemen, if you want to represent this quotient in standard complex number form, we would split this up and put 19 over 17 plus 9 over 17 and then multiply that by I. This is standard form for a complex number, A plus BI form. There you go. We have just divided 5 plus I by 4 minus I. We've done so by rationalizing this denominator by getting rid of I by multiplying top and bottom of fraction by the complex conjugate of 4 minus I, which is 4 plus I. That's how we divide it. So to divide complex numbers means to get rid of I in the denominator. That's what it means. All right, you guys ready for classwork number 1? Classwork number 1. All right, just remember for classwork or any email, you always want to, have your label and your subject line as math, hit your space key and then just type in 130. Okay, so math, hit your space key on your calculator, your computer rather, your space bar, just type in 130. And you can put classwork 1. This is for September 20th. All right, I want you to try a couple of these. Problem number 1, I want you to simplify this. Square root of -3 multiplied by the square root of 11 minus the square root of -7. Problem number 2, I want you to simplify this. 3 subtract the square root of -5 multiplied by 4 plus the square root of -5. Problem number 3, I would like you to divide 8 minus 5I, divide that by 13 plus 2I. There you go, ladies and gentlemen. See what you can do on those, okay? Classwork number 1. Okay, so these are the solutions of classwork number 1, 1, and 2. I did not have my recording going. Okay, now it's going. All right. All right, number 3, when you divide these complex numbers, dividing complex numbers comes down to getting rid of I in the denominator by multiplying top and bottom by the complex conjugate of the denominator, which in this case would be 13 minus 2i. Then you're going to multiply your numerators out by foiling this all out, gathering together like terms, simplifying. The denominators, since they're complex conjugates, is easy to multiply together. You just square your first term, square your last term, and then put a minus sign between them. It's easy to multiply conjugates together. Anyways, doing all the simplification here, ladies and gentlemen, replacing I squared, of course, with -1. Going through all this simplification here. In the end, I did split this up because I want my final answer expressed in the form of like A plus BI form. So I did split this fraction up and got it down to that. Did anybody persevere to the end to get something like that?
I miswrote a 5 as a 3 and then
It happened.
mismultiplied.
You got to concentrate. I'll tell you, there's a lot of room for error in a problem like this, ladies and gentlemen. And, you know, the deeper you go in math, the longer the problems get, and the more chance there is for error. And that's why the problems not necessarily become more difficult the higher you go in college. They become longer. And the longer they become, the greater chance there is for mishap. All right, so that's classwork number 1. If you can, email that to me by midnight tonight, that would be great. That'll give you your classwork credit, ladies and gentlemen, for the day. All right, one last section today is section 1.4, and it is going to involve solving what are called quadratic equations, okay? What does a quadratic equation even look like? Well, in general, this is what a quadratic equation looks like. It's always a second degree equation where we do have a second degree term, x is to the second power, and that's why we call this a quadratic equation. We have a second degree term for our highest degree term. A, B, and C are just real numbers. And this is what a quadratic equation looks like. If we did not have our quadratic or second degree term, this equation would collapse down to being an ordinary what? Linear equation. Do you agree? First degree equation, of which we solved those eons ago in elementary algebra. Later on, we're going to learn how to solve second degree equations called quadratic equations. Ladies and gentlemen, these equations will always have 2 solutions. Not 1, but 2 solutions. They may be real solutions, or they could be complex conjugate solutions. They could be real solutions, 2 real solutions, or they could be complex conjugate solutions. All right. Many, many ways of solving quadratic equations. Most popular method is the factoring method, if you're able to factor. Factor method. Then we have another technique called the square root method. If those fail, we have another technique called completing the square method. And your favorite method, ladies and gentlemen, is the quadratic formula. Do any of these ring a bell? These methods of solution?
Yeah.
Right? Those are all the different ways of solving quadratic equations. In all honesty, the fastest way to solve a quadratic equation, if we're able to do so, is the factoring method. That's the quickest way. But unfortunately, we're not always able to factor, in which case we have to resort to some other technique. But factoring is the quickest way to go if your equation is factorable. So I'm going to demonstrate a couple of each of these methods of solution for solving these second degree or quadratic equations that, again, must always have 2 solutions. It's either going to be that they have 2 real solutions or they're going to have 2 complex solutions. And if they have 2 complex solutions, they always come in conjugate pairs. Ladies and gentlemen, the deeper we go into this course, we're going to learn how to solve eventually 3rd degree, 4th degree, 5th degree, 6th degree polynomial equations. And we're going to run into a powerful theorem called the fundamental theorem of algebra that guarantees when you solve an nth degree polynomial equation, you're going to get n solutions. This is a second degree equation. Therefore, we're going to get 2 solutions. Okay. All right. So here we go. Let's look at the factoring method first. All right. So let's try this one out here. Solve by factoring. Here's our quadratic equation. X squared plus 5x plus 6 is equal to 0. In order to use this factoring method, ladies and gentlemen, our equation must always be zeroed out. So you got to get your equation set equal to 0 to utilize this factoring method. Notice my equation is already set equal to 0. We're good to go. And as the name suggests, we're going to try to factor completely the left side of this equation. Notice there's nothing we can factor out of all 3 terms. And so therefore we have to employ the fact that it's a what? Trinomial. Easy type of trinomial, one with a leading coefficient of 1. Therefore, how does this factor? Can you give me a couple factors of the constant term, positive 6, that sum up to the middle coefficient of positive 5?
3 and 2.
3 and 2, or 2 and 3. Therefore, this left side immediately factors into the product of these 2 binomials, x plus 3 times x plus 2. Now that the left side is completely factored, ladies and gentlemen, we can tap into a theorem called the zero product theorem. This theorem, unlike most theorems, is extremely intuitive. It says that if you take the product of two factors and you get a product of 0, this theorem then guarantees that either what? Either the first factor is 0 or the what? Second factor is 0. Does that make sense? That would be the case? So look at, we got the product of 2 factors is equal to 0. According to this theorem here, I should be able to set these factors equal to 0. So we set x plus 3 equal to 0, and we set x plus 2 equal to 0. Now we have 2 simple first degree equations to solve. Subtracting 3 from both sides to solve this first degree equation, we get x is equal to -3. There's one solution of your quadratic equation. To find the necessary second solution, we solve this linear equation by subtracting 2 from both sides, and we get x is equal to -2. Ladies and gentlemen, we now have the 2 solutions to this quadratic equation, -2 and -3. This technique was called what? What technique did I just demonstrate for solving this quadratic equation?
Factor.
The factoring method. Everybody see the factoring method there? Factoring method in action, because we're able to factor the left side. That's the factoring method. Okay. All right. Questions on that problem there? Notice these are both real solutions. They're real numbers. All right. Try another one here. Solve by factoring. We have z squared is equal to 25z. Make sure you put a slash through your z's, otherwise they can look like 2s. Ladies and gentlemen, what was the requirement in order for the factoring method to even work? Our equation has to be set equal to what?
0.
So to zero this equation out, we're going to drag this 25z, this linear term, over to the left side of our equation. How? How algebraically do we move a positive to the other side? We subtract 25z from both sides of our equation. When you subtract it from the right, it goes to 0. And of course, the left, we also subtract 25z. Now that my equation is set equal to 0, we ask ourselves, can we factor this left side? We want to completely factor the left side. Ladies and gentlemen, notice, what can I factor out of both terms here?
Z.
See?
All right,
Z.
looks like we can factor out a z. And when we factor a z out, what do we leave behind?
Z minus 25.
Z minus 25. Now that our left side is completely factored, this is not the difference of squares, by the way. Z is not a perfect square. Now that our left side is completely factored, we set both factors equal to 0. And we solve both simple first degree equations. This one is already solved. So one solution to our quadratic equation is 0. The other solution is found by solving this equation for z, and we get 25 as being another solution. And we are done. We have solved this quadratic equation for its two solutions. It's called the factoring method. Is this factoring method making any sense here?
Yes.
Yes.
So obviously we have to know how to factor polynomials in order for this technique to work here. Okay. All right. So that's called the factoring method. If I have n plus 2 times n plus n minus 4 rather equal to 27. Suppose you want to solve by factoring. Now this doesn't even look like a quadratic equation. I don't see n squared. Well, you'll see n squared surface in a moment. But what you don't want to do is you don't want to set both these factors equal to 27. Why would it be absurd to say that this factor is 27 and this factor is 27? If you say this factor is 27 and this factor is 27, then you would be admitting to saying 27 times 27 equals 27. Is that true? No good. When do we set our factors equal to something? When that something is what? Only when it's what? 0. So the first thing we need to do here is get this equation zeroed out. So we're gonna have to subtract 27 from both sides of this equation. Now our equation is set equal to 0. Now we got to FOIL this out. We don't have any choice. So we got n times n is n squared, n times negative 4 is negative 4n, 2 times n is 2n, 2 times negative 4 is negative 8. Simplifying the left side by combining like terms, we got n squared, negative 4n plus 2n is minus 2n. Negative 8 subtract to 27 is negative 35. And ladies and gentlemen, now can I factor my left side? Notice it's an easy type of trinomial to factor. I need two factors of negative 35 that add up to negative 2. Do they exist?
Yes.
What would they be?
Negative 7 and 5.
Negative 7 and 5. So the left side immediately factors in n minus 7 times n plus 5. Now that my left side is completely factored, we set both factors equal to 0. And then we solve the resultant first degree equations. Solving this equation for n, we get n is equal to 7. That's one solution to your quadratic equation. Subtracting 5 from both sides to solve this linear equation, we get n is equal to negative 5. There's your other solution. We're done, ladies and gentlemen. So negative 5 and 7 are the two solutions to this quadratic equation. Initially, it doesn't even look like this is a quadratic equation, but when you multiply this out, you can see the second degree term surface here. So it is a second degree or quadratic equation. Okay, that's why it must have two solutions. Questions how we solve quadratic equations via factoring, ladies and gentlemen. Just got to make sure your equation is always set equal to what first?
0.
0. And then you try to completely factor the other side. All right. There's another technique, ladies and gentlemen. It's called the square root method for solving a quadratic equation. Square root method. This method requires that your quadratic equation be in the form of something squared equal to some real number. Your quadratic equation has to look like this in general. We have some squared quantity equal to a real number. If that's the case, to solve for the variable, you take the square root of both sides of the equation. But this is the kicker we cannot forget. Please highlight this in your notes. When you take the square root of a number side, you must always have the plus or minus square root of the number side. Don't forget the plus or minus. The reason why is because these quadratic equations must have two solutions, and this plus or minus notation ensures you're going to crank out two solutions. The square root of x squared is just x, and so our two solutions in general to a quadratic equation that looks like this, using the square root method, would be x is equal to positive or negative square root of this number c. This is called the square root method in general, for solving a quadratic equation. It's a rather restrictive method in the sense that your equation has to be in this form, though. All right, so that's somewhat restrictive. Let's look at maybe one or two of these. Okay. All right, here we go. Here we go. So we're going to try to solve by square root method. SRM, I will abbreviate it, square root method. All right, here we go. Here's one. Let's have 8p squared plus 72 is equal to 0. We want to solve this quadratic equation for its two solutions using the square root method. How do we do that? Well, what we're going to have to do is we're going to have to isolate the squared quantity on the left side of our equation. That's to say we have to isolate p squared. So we got to get everything else on the right side of the equation, try to get p squared all by itself. How do I move in that direction? First move, ladies and gentlemen, what is it? How do I solve?
Divide by 8?
What's that?
Is it divide by the 8?
You could, but before we do that, let's just move the 72 over to the right.
72.
Oh, okay.
Yeah, let's subtract 72 from both sides, okay? Then we'll divide by 8, all right? So hold on to that thought. All right, so therefore we got 8p squared is equal to what? Negative 72? Now we divide, you are right, both sides by what? 8. So therefore p squared is going to be equal to what? What's negative 72 divided by 8? Negative 9?
Yeah.
Now, ladies and gentlemen, how am I going to solve for the two solutions of this quadratic equation? How do you get rid of the square? We take the,
Square root.
we hit both sides with the square root function, don't we? That's why they call it the square root method. So we're going to have to take the square root of the left side of our equation and the square root of the right side. But I just made a mistake. I lost 50% of my solutions. What happened? What did I forget?
Plus negative. I mean,
Plus or minus, ladies and gentlemen,
Yeah.
square root of the number side. Don't forget the plus or minus. That's often forgotten. Please highlight that in your notes. It's got to be the plus or minus square root of negative 9. So therefore, the square root of p squared is just p. So our two solutions for p are going to be positive or negative square root of negative 9. Since we have a negative underneath our square root, we extract what? I times the square root of positive 9. So therefore, our two solutions to this quadratic equation for p are going to be plus or minus 3 what? I square root of 9 is 3. Ladies and gentlemen, these solutions to this quadratic equation are not real solutions. They're complex conjugate solutions. These are your solutions. This is a compact way of saying p is equal to 3i or p is equal to what? Negative 3i. This is a compact way of saying positive or negative 3i. All right. So that quadratic equation has two complex conjugate solutions. That technique is called the what method? The
Square root method?
the square root technique, correct? Notice that square root method, because we're ultimately taking the square root of both sides here. All right, that's why we call it the square root method. But again, your square root method requires that your equation get down to this first before you hit both sides of the square root. Something squared equal to a number. So notice we had to get it down to something squared is equal to a number. Then we take the square root of both sides. Okay. All right. Got that one? All right. Let's try this one. Solve by SRM. What does that stand for? SRM.
Square root method.
Yeah, so let's try to solve this by the square root method. Here it is. We got a minus 1/3 quantity squared is equal to negative 47/9. We want to solve this quadratic equation for its two solutions using the square root method. Now, why am I even calling this a quadratic equation? I don't really see a squared anywhere. But ladies and gentlemen, if I was to do this, which I don't want to do this, but if I was to take a minus 1/3 and multiply it by itself, do you agree that a squared would surface? Isn't that true?
Yes.
So this is a quadratic equation. Doesn't look like it initially, but it is. It's going to have two solutions. But what you don't want to do is multiply this out. You don't want to square a minus 1/3 Because you're gonna have to turn right back around and factor it back in its present factored form to employ the square root method. Notice we already got this thing set up for us to apply the square root method. We got something squared equal to a number. That's the form we need for this method to work. So immediately we hit both sides with the square root function. And don't forget to take the plus or minus square root of the number side. Now, what's the square root of this quantity squared? What does the left side simplify to? Anybody? The square root of a minus 1/3 squared is going to be just a minus 1/3. The right side, we have the square root of a negative number, meaning we must bring I out. Plus or minus I times the square root of positive 47 over 9. All right. Now, as I'm going to get a by itself, we're going to add 1/3 to both sides of this equation. Notice how I add it to the right side. I precede the plus and minus business with the 1/3 I'm adding to the right side. And 1/3 dive out on the left side, leaving us with a. On the right side, we have 1/3 plus or minus. Can we simplify the square root of 47/9? We were taught in the past never to leave a fraction underneath a radical, so we would use our quotient rule of radicals and rewrite this like this. Almost there. So we got a is equal to 1/3 plus or minus. Oop, I forgot my I. Sorry about that, ladies and gentlemen. Plus or minus I times the square root of 47 over what? What's the square root of 9? 3?
Yeah.
Everybody see that? So our two solutions of this quadratic equation happen to be complex conjugate solutions. One solution is 1/3 plus I square root of 47 over 3. And the other solution is the complex conjugate solution, 1/3 minus I times the square root of 47 over 3. This is this is a more compact way. Do you agree? Of representing these two solutions? This is a more compact way, more compact way. I don't care if you represent them this way or if you leave it in compact form like this, either one. So this method I am showing you, ladies and gentlemen, is called the what technique? It is called the square root what method? Do you agree? For solving a quadratic equation. Unfortunately, it's a restrictive method in the sense that our equation has to be in the strict form where we have something squared equal to a number. So it is somewhat of a restrictive technique, okay? But nonetheless, if we had our quadratic equation looking like this, we would probably want to use a square root method. That'd be the quickest way in this situation, okay? All right. Okay. So I showed you a couple using the what? Square root method, didn't I? Square root method. We just have two more techniques to demonstrate to you, ladies and gentlemen, the completion of the square method and the quadratic formula. All right, suppose I gave you this quadratic equation and I wanted you to solve it. X squared plus 8x plus, let's see here, plus 9, and I wanted you to solve this quadratic equation for its two solutions. Wait a minute, I'm sorry, equal to 0. No, it's got to be an equation, my bad. All right, so here's a quadratic equation. We want to solve for the two solutions of x. What techniques have we seen so far? We've seen the factoring method and we've seen the square root method. The square root method really does not look like it applies here because we got this linear term in the way, this first degree term. But if I did not have this 8x here, then I could subtract 9 from both sides. Do you agree? And then use the square root method?
Yes.
But I got the 8x in the way. We see that linear term in the way there? Because we got the 8x in the way, the square root method initially doesn't look like it's going to apply here. Could I use the factoring method? Might this trinomial be factorable? Because if it is, why not go that route? Notice it's an easy type of trinomial. I need two factors of 9 that sum up to 8. Do they exist?
No.
No.
Yeah, we got a problem here. The only factors of 9 are 1 and 9 and 3 and 3. Of course, we got negative factors we don't consider here because we got a positive here, but do you agree none of these factors add up to 8? 1 plus 9 is not 8, 3 plus 3 is not 8. Factoring doesn't work. Can't use the factoring method, it fails. So ladies and gentlemen, how are we going to solve this quadratic equation for its two solutions? Because it does have two solutions. How are we going to find them? Well, there's another technique, ladies and gentlemen. It is called completing the square method. Not a big favorite among students, but the completion of the square method, believe it or not, is also utilized at time to time in calculus. And for that reason, if you're going into calculus, it would be wise to know how to complete the square. Completing the square method, ladies and gentlemen. What is this method all about? I'm going to come back and I will solve this equation via completing the square, but I'm going to take a little sidetrack, okay, because I want to show you what completing of the square is all about. In general, if I have a binomial that looks like this in general, ladies and gentlemen, if I have a binomial that looks like this in general, B is some real number. What I can do is I can add a very special number to this binomial to transform it into a very special very special type of trinomial called a perfect square trinomial, one that can always be factored. But what's that special number that we add to this binomial to achieve that? Well, here's what we're going to do. We're going to transform this binomial into a very special type of factorable trinomial called a perfect square trinomial by adding to this binomial the square of half of the linear coefficient. This plus b is called my linear coefficient. So what I would do first of all is take this b and I would take half of it. That's to say I would divide b by 2 or multiply b by 1/2. Look at when you divide a number b by 2, it's the same thing as multiplying the number by 1/2. Do we buy that? Same thing? Okay. All right, so ladies and gentlemen, we're going to take half of our linear coefficient. We're going to square that number. Now, by adding this special number to my binomial, I claim that this trinomial I created now is factorable. It's always factorable. And how would this factor? Well, this trinomial here would factor into x plus b over 2 times x plus b over 2. That's how it would factor. In fact, since these factors are identical, we can write this in more compact form as x plus b over 2 quantity squared. And for that reason, we call this trinomial we created by completing the square on this binomial, we call this a perfect square trinomial. Perfect square trinomial because it is the square of a binomial. This perfect square trinomial can be factored as a square of a binomial. That's why we call this a perfect square trinomial. So what was the magic number we added to this binomial x squared plus bx to transform it into this magical trinomial that factors? We added to it the square of half of our linear coefficient. The square of half of this number here. That always works. That's called completing the square on a binomial. So we're going to show you now how to solve this quadratic equation by completing the square on the variable x. Okay? So let's try to do this. So we're going to solve x squared plus 8x plus 9 equals 0 by the square root method. Square root method abbreviated as SRM. Wait a minute. That was the last thing. We're done with the square root method. We're going to abbreviate completing the square method as CTM. Completing the square CTS, I'm sorry. So we'll abbreviate completing the square method as CTS, completing the square, okay? Completing the square. So we're going to try to solve this quadratic equation by completing the square on it. So how do we do that? What's the first step? Well, the first thing we need to do is move this constant term over to the right side. How do you move a positive 9 to the other side?
Subtracting.
So let's minus off 9 from the left and also from the right. When we minus it off from the left, it's gone. When we minus it off from the right, we're left with 0 minus 9 or negative 9. So the first thing is just move this constant term over to the right. Now that we've done that, ladies and gentlemen, we leave behind the binomial on the left side of our equation. We're going to now complete the square on this binomial. And what number do I add to it to complete the square on it, to transform it into that magical type of trinomial called a perfect square trinomial? What do I add to this binomial? Well, I'm going to take half of my linear coefficient, which is 8. So I'll have 8 divided by 2, or 8 times 1/2, and then I'll square that number. If I add that number to the left side of my equation, however, I must add the same number to the right side to maintain equivalence. This is called the completing of the square step of this procedure. We're literally completing the square on this binomial to transform it into a very special type of trinomial, one that can always be factored. All right, let's clean this up. We got x squared plus 8x plus 8 divided by 2, ladies and gentlemen, is 4. And so we'll have plus what, 4 squared at the end? The right side is negative 9 plus what, 4 squared? What is 4 squared? Might as well just simplify it over here. 4 squared is what, 16? What's so special about this trinomial I created on the left side, x squared plus 8x plus 16? What's so special about it? It can be what? Factored. Do you agree? It's a perfect square trinomial. Why? Because we completed the square in this binomial. Why? By adding this special number to it. Perfect square trinomial. The right side, negative 9 plus 16 is 7. Ladies and gentlemen, does this trinomial factor? The answer is absolutely yes. What does it factor into? X for your first terms. And what did I square to get 16? I squared 4. So this trinomial factors in x plus 4 times x plus 4. Or x plus 4 squared. That's why we called it a perfect square trinomial, because this trinomial factors as the square of a binomial. That's why this is called a perfect square trinomial. And it resulted from us completing the square on this binomial right here, completing the square of it. What's going to take us the rest of the way, ladies and gentlemen? What method? We now fall back and use the what? Square root method. Hit both sides with the square root function. So we take the square root of the left side. Take the positive negative square root of the right side. I'll have to finish up here. The square root of x plus 4 squared on the left is just x plus 4. The square root of 7, unfortunately, on the right side cannot be simplified. Just leave it in exact form. Please do not turn it into a decimal. Leave it like that. Finally, to solve for x, we subtract 4 from both sides. So x is equal to negative 4 plus or minus the square root of 7. We are done. These are your two solutions in exact form for this quadratic equation up here. And this entire technique was called the what method, ladies and gentlemen?
Completing the square method.
Completing the square technique. Do we see that there?
Yes, in fear of sounding silly, I have a question.
Go ahead.
So when you do the 8 over 2,
Mhm.
now when we do this, let's say it was a 16x, would we do 16 over 2
That's
squared?
correct. Yeah, that's correct. Look at in
So it's
general.
always over 2.
Yeah, see, in general, whenever we have
Okay.
a binomial that looks like this, to complete the square in this binomial, we always take what, half of whatever this number is, right?
Yes.
And then we square it. Okay?
Okay.
In
Yes.
general, that's what you always do. And by doing that, then the trinomial you create will always be what? Factorable. Do you agree? Always.
Yes.
Always. That's why we do that. To create a trinomial, it's always factorable. Okay? That's the gist of the whole completing the square method, is to create a trinomial that can always be factored. And it always works too. It seems magical, but it always works. All right, now, Liz, I'm completing the square to solve this quadratic equation for this example was an easy one. Here's why. We were blessed in many ways with this problem. Number one, we had a leading coefficient of 1. This is the easy type to complete the square on. Number two, our middle coefficient or linear coefficient is a nice what? Number that's divisible by 2. Do you agree? 8 is nicely divisible by 2.
Yes.
You give us the whole number of 4. Do you think we're always going to have these luxuries?
No.
No, we better look at a more difficult one to complete the square on, one that does not have a leading coefficient and one that does not have a nice linear coefficient that's nicely divisible by 2, because they do exist out there. So we better look at one that's a little messier. But does this one nice one make sense though? What happened? The easy one, the nice one? Okay, so what we did here is pretty much the same thing we're gonna do even on difficult ones. But we better look at a difficult one. So let's try to solve by completing the square. And let's give us one that's a little bit more difficult. How about 4t squared plus 3t minus 8 is equal to 0. We will try to solve this quadratic equation by completing the square. In fact, I think you will agree that completing the square is the only method that's going to work for us at this point in time, because notice we cannot factor this left side. 4 times negative, you can't factor anything out of all 3 terms. And 4 times negative 8 is negative 32. But ladies and gentlemen, there are no factors of negative 32 that sum up to what? Positive 3. So this left side is not even factorable. So you can't use the factoring method. Doesn't look like the square root method is applicable at this time. We're going to therefore have to solve it by using the completing the square method. All right, the first step is to move the constant term over to the right side. So we add 8 to both sides. Kick the 8 over to the right. So therefore we got 4t squared plus 3t is equal to 8. Now, unlike the last problem where we had a nice leading coefficient of 1, we no longer have 1 for a leading coefficient. Before we're able to complete the square on this binomial, therefore, ladies and gentlemen, we need to force a 1 in front of t squared. The only way to do that legally algebraically is to divide both sides of your equation by 4. So I'm going to divide every term on the left side by 4. And I'm going to divide every term on the right side of the equation by 4. Now, 4t squared divided by 4 now is 1t squared, and that's what we wanted, is 1 in front of t squared. Unfortunately, we've created a monster here in front of t. Now we got 3/4. Hey, look at it, got a little bonus on the right side. 8 is evenly divisible by 4 to take it down to 2. Please do not convert fractions into decimals. You think fractions are messy. If you convert them into decimals, it's going to be extremely messy. Always leave fractions as fractions when you complete the square. You can reduce them, but leave them as fractions. No decimals. All right, so ladies and gentlemen, now we're able to complete the square on this binomial in t because we have 1 in front of, as our leading coefficient. What is that magic number I have to add to this binomial to transform it into a perfect square trinomial? Anybody remember? I have to take half of this 3/4. Now, on the previous problem, I divided my linear coefficient by 2, but if we divide 3/4 by 2, that's going to look messy as heck, isn't it? Remember I said, ladies and gentlemen, an alternative dividing your linear coefficient by 2 is to also what? Another way is to look at it is to what? Multiply it by 1/2. Do you agree? Don't these mean the same thing? Okay, so in this case, since we got 3/4, let's multiply 3/4 by 1/2. That's equivalent to saying we divided 3/4 by 2, and we're going to square that. Guess what? Must add the same number to the right side of my equation. Back on the left side now. All right, let's try to simplify this a little bit more. We got t squared plus 3/4 t. 1/2 times 3/4 is going to be 3/8. On the right side, we're likewise going to have 3/8 squared. Ladies and gentlemen, this is a very special type of trinomial. It's one that can be factored. In fact, what does it factor into? Well, it factors into identical binomial factors, namely what? T plus, what am I squaring to get my last term? 3/8? So this trinomial is going to factor into t plus 3/8 times t plus 3/8. Left side is completely factored. The right side, we would clean this up here. We got 2 plus 3/8 times 3/8 is 9/64. The left side can be rewritten more compactly as t plus 3/8 squared. The right side, this 2 sits over 1, need a common denominator of 1 and 64, which is 64. What's an equivalent fraction of 2 over 1 that has 64 for its denominator? We would multiply top and bottom of 2 over 1 by 64 to give us 120, to give us 128 over what, 64? As another name for 2, plus 9 over 64. Left side is t plus 3/8 quantity squared. What's 128 plus 9 over 64? 137, is that correct?
Yes.
Ladies and gentlemen, do you agree now, since we have something squared equal to a number, it's time to what? Hit both sides with the square root? So we take the square root of both sides, not forgetting that the right side must be always the plus or minus square root of the number side. Don't forget that. You agree the left side of this equation simply collapses down to just what? T plus 3/8. The right side is a little bit messier, but do you agree the 64 in the denominator can be brought out as an 8? The square root of 64 is an 8. So we got plus or minus the square root of 137 over what? 8. You still with me?
Yes.
Finally, ladies, I'm going to solve for t. We subtract 3/8 from both sides to get t by itself. Therefore, our two solutions for t are going to be t is equal to negative 3/8 plus or minus the square root of 137 over 8. Leave your answers like that. There you go. You got your two solutions to that quadratic equation way back up here. All right. That technique is called completing the square method on a nasty type of quadratic equation, one where we don't have a leading coefficient of 1 rather, and one where we don't have a nice multiple of 2 rather for our middle coefficient or linear coefficient. But nonetheless, does that make sense, that procedure there? Messy, but it worked, did it not? Messy, but it worked. Okay. So what do you think about the completing the square method, ladies and gentlemen? Not a big favorite, is it?
No.
Not a big favorite, a lot of work, okay? But you're gonna love this last thing. It's called the quadratic formula, ladies and gentlemen. The quadratic formula, believe it or not, is made possible by the completing the square method. I did make a video in the past showing how the quadratic formula is derived by completing the square in general on a quadratic equation that looks like this. Maybe I'll find that video and upload it in case you're interested in knowing how the quadratic formula even comes into existence, okay? It is a rather lengthy derivation, but I did film it for one of my previous classes, and I can post it in case anybody's interested in seeing the derivation, all right? The derivation is in your textbook also, I believe, but I think it's funner just to listen to myself. I don't know. That's just me, though. I'm biased, though. All right, ladies and gentlemen, in general, when you have a quadratic equation like this in general, you can always solve it by what is called the quadratic formula. It will solve any quadratic equation just so long as it is in this form. The left side needs to be in descending order, second degree term, first degree term, constant term, and it better be equal to set equal to 0. This would be your quadratic formula. Your solutions x are going to be the opposite of the linear coefficient, whatever b is, plus or minus the square root of b squared minus 4 times the leading coefficient a times the constant term c, all divided by 2 times the leading coefficient of a. That is called your quadratic formula. How many people have ever seen that before?
I have.
I have.
It'll solve any quadratic equation. Doesn't matter how messy or nice it is, as long as the equation's in this form. In fact, let's convince ourselves. What was the last one I just solved, ladies and gentlemen? What was that last one we just solved? We went through the completing the square method. It took a long time. What was it? Can you read that equation off to me? The last one. That last one. Anybody got it?
4t squared plus 3t minus 8 equals 0.
Plus 8 equals 0. Okay. We're going to solve this quadratic equation by the what? The quadratic formula. QF is the abbreviation for quadratic formula method, ladies and gentlemen. All right, to use this method, it's simple. First of all, my equation is zeroed out. It needs to be. And notice my left side's in descending order, second degree term, first degree term, constant term. I need to identify what, ladies and gentlemen, what my A is, what B is, and my C is for the purpose of the formula. What's my A?
4.
A is 4. What's my B? My linear coefficient?
3.
Positive 3. What's my constant term?
8.
Positive 8. Careful, if you got minus signs in here, like if this was a minus 3t, then my B would be a negative 3. If this was a minus 8, my C would be a negative 8. Pay attention to your signs too with this formula. Unfortunately, sign mistakes are the most prevalent mistakes when using this technique. Careful on the signs. Ladies and gentlemen, my two solutions T are going to be in the form of the opposite of B, but B is what? 3, right? So I have the opposite of 3 plus or minus the square root of B squared. What's B? 3, so 3 squared. Minus 4 times A times C. What's A? A is 4. C is 8. All divided by 2 times the leading coefficient A. A is what? 4. Does everybody understand how I substituted the numbers in where they belong into the quadratic formula? Now it's just a matter of, can we go through the arithmetic without messing this up? Careful with all your signs. All right, 3 squared is 9. So we got 9 minus 4 times 4 is 16, and 8 times 16 is 128. Wait a minute here. Was this the last problem we did?
I think it was supposed to be a -8 instead of.
It was supposed to be a
positive.
-8, wasn't it?
Yeah.
Son of a brachiosaurus. Hold on a second. That should be a -8, ladies and gentlemen. We can fix this. All right, no big deal, no biggie. All right, so that's going to be a -8. All right, so we got 9, subtract 4 times 4 is -16, but -16 times a -8 is plus a what? Plus a 128, I believe. 2 times 4 is 8. Do you agree my two solutions for T are going to be -3 plus or minus the square root of what? 137 over what? 8? Ladies and gentlemen, is that what we got for our two solutions using the completing the square method?
Yes.
I think
Yes.
it was, right? We just split this up, correct? Recognize these? Remember, these are the solutions we got by solving that by completing the square method. Look at how quick the quadratic formula is. You see, a lot quicker, isn't it, in completing the square? Well, you be the judge. What do you think? This or this? You know, what method is quicker? Obviously, the quadratic formula is quicker. But ladies and gentlemen, this powerful formula called the quadratic formula was made possible by completing the square on this. And I will post that video showing the derivation of how you complete the square on this in general to derive your quadratic formula. Quite a derivation, okay? Everybody see that there? How many people use the quadratic formula here to solve quadratic equations?
I have.
All right, okay. Now, if this quantity underneath the square root ever turns out to be a negative number, what do we have to bring out? If this is a negative underneath the square root, we got to bring out what character? I. Yep, your solutions then would be complex solutions, not real. Okay, but for this problem, since my quantity underneath my square root, and that quantity has a name, it's called the discriminant of my quadratic equation. Since my discriminant is positive, I have real solutions. These are real solutions. You don't see I anywhere. They're not complex solutions. They're real solutions. Now, if this was a square root of -137, then I would have to bring I out. It'd be I times the square root of 137 then, okay? But these are real solutions. All right. The bottom line is the way it works here. I'm going to leave. I'll leave you with this one last thing here. I know I worn out my welcome. It's called the discriminant of a quadratic equation. Discriminant. The discriminant of a quadratic equation, ladies and gentlemen, is the quantity underneath the square root, this b squared minus 4ac. If, ladies and gentlemen, b squared minus 4ac is negative, meaning less than 0, then you're going to have complex solutions. Complex solutions. If your discriminant underneath your square root is b squared minus 4ac, if it's positive, meaning greater than 0, then you're going to have real solutions. Okay? To say we have complex solutions mean you would see I in your solution. Real solutions, you're not going to see I. That's called a discriminant. This quantity underneath the square root. Just by looking at the discriminant, you can predict what your solutions of your quadratic equation are going to be, whether they're going to be complex or real. Again, if your discriminant's negative, you're going to have complex solutions. I will be present in your solutions. If your discriminant's positive, you're going to have real solutions. No I. Make sense? Wow. You know, it's amazing. It's always like I'm always fighting the clock with this class. I don't know, ladies and gentlemen. It just seems like there's such a volume, you know, to get through. It's just unbelievable. So there it is, ladies and gentlemen, and I think that that will do it for today. Okay. I will obviously, you know, give you another textbook homework assignment, but I'm going to try to, you know, cut down on the volume of problems that I'm throwing at you. You can always do more problems in your textbook. If you feel you need extra practice, then you take it upon yourself to do more practice, ladies and gentlemen. Okay. But, you know, I'm going to start cutting down on the volume a little bit. I think the emphasis, believe it or not, is going to be maybe from the textbook, though. Where, you know, because they offer you more, I think, more choices in the textbook, but then that means Alex, I'll give you much fewer problems on Alex to play around with. Okay. Hey, you know, when you're doing your homework assignment on Alex, you can always click on a button. I think that it says what? Show me another one. Does it say show me another one where you can work another one out? Is that true on Alex? I think you can do that on Alex. If you want to work another practice problem out on Alex, you can click on a button that says show me another one or do another one.
I believe so, because if you get it wrong, they'll let you try again.
Yeah, try again. I think you still have the option of even doing another one, you know, if you want more practice on that. I think
Yeah,
have
you
that
do.
option. So that's awesome. I mean, there you go. I mean, if you want to do more practice on Alex, you know, just click on the button. I'm not going to, you know, bar you from doing that, but I'm going to try to cut down for the bare minimum requirement. Okay. All right, ladies and gentlemen, I got to get out of here. You guys, you have a great day. Okay. If you have any other questions or concerns, I'll be on the line for a couple minutes if you have any questions. All right, take care. See you hopefully on Wednesday.
See ya. Do we have assigned homework on Alex yet, or is it only just the homework out of the book right now still?
Well, I have been posting some assignments on Alex. It goes back to, you know, our first section that we started. I think it was like was it R3, R4 or something? But I think there's 3 homework assignments on there presently. Okay.
Okay.
They're all due on October 20th by midnight. I mean, so it's like you got time to do them. You know, you got a whole month, in fact. But, you know, you always probably want to try to stay up with it and try not to procrastinate. Okay.
Okay, thank you.
All righty.